Okay, let's talk about our units now. If I say I owe you 1,000, what does that mean? I owe you 1,000 what? Do I owe you $1,000? Do I owe you 1,000 pennies? Do I owe you 1,000 high fives? Like what does that mean? Right? We have to give a measurement a unit for it to mean anything. And to this end, we choose base units. All our base units are going to be metric. We are scientists here. Scientists use the metric system. Everything is base 10, and the metric system is derived from water. So the meter, the liter, and the kilogram are all defined from each other based off of water. So a liter of water weighs a kilogram, which is a cubic deciliter. Um, that decimeter, excuse me, that conversion makes it so that this is a pretty straightforward measurement system. Also, all of our conversions are base 10, so they're always orders of 10, like 100 or 1,000 instead of feet to inches being 5,280 for some reason. So it makes it doing conversions easier. So our base units that we're going to use here in physics are the meter, the liter, the second, for charge, the coulomb. Um, Often we'll see volume in cubic meters as well. Uh, Instead of in liters. You could use either depending on what the constants or the values you're given. And something I want to make an important note of is that mass in physics, its base unit is the kilogram. So in chemistry, the base unit for mass is the gram. In physics, it's the kilogram. And the reason that it's the kilogram in physics is because we often are going to be dealing with a lot larger objects. In chemistry, you're usually dealing with samples that are smaller or way less. So in physics, because we are dealing with large amounts of stuff, usually everyday objects, we need something analogous to the pound, which is going to be the kilogram. I'm going to pass it over to live action Asa now to show you guys an example of all of these units. Hi there, live action Asa back. I'm here to demonstrate for you what all of our base units in the metric system look like. I'm assuming that all of you are very familiar with how long a second is, but being in the United States, we usually are used to using English units. That is, feet, pounds, ounces. So I wanted to kind of give you a little bit of perspective on what all of our metric units look like. So a meter is this long. It's a little over 3 feet. This is a meter stick. So this is exactly the length of 1 meter. If I'm measuring something on a smaller scale, like my thumb, I might use the centimeter side of this, hundredths of a meter. If I wanted to use a large estimate, like distance between 2 cities, I would use 1,000-meter increments to the kilometer. A liter is a measurement of volume. This is a liter of water right here in my hands. It's about 1,000 milliliters inside this beaker. I like to think of it as being half of a 2-liter bottle of soda. And then lastly, we have the kilogram. Now, if you've taken chemistry recently, you probably are familiar with grams being the base unit for measurement, but here in physics, we usually are talking about larger objects. So we want something that is analogous to the pound in the English system, which is the kilogram. This bag of powdered sugar that I have in here for some reason is about a kilogram. It's a little under a kilogram. A kilogram is about 2.2 pounds. For those of you who are familiar with the English standard system. By the way, I meant to mention earlier also, a liter is about a quarter of a gallon. So for those of you who are used to English units like we use here in the United States usually, those are just some examples of what the metric equivalents are. Thanks, live action Asa. Um, so here we are back to units. We also, in addition to our base units, we have derived units too. So derived units are made out of base units. Basically, if we have a quantity that is calculated, something that we're not measuring directly but calculating, we're going to just mash together our base units to determine the units for our calculations. These are usually a pain to say, so we will often name these a nickname after a scientist. So for instance, velocity is distance over time. Well, that's going to be the unit for distance, the meter, over the unit for time, the second. So velocity, being distance over time, is going to be meters over seconds. Density, mass over volume, is going to be in kilograms over cubic meters. You could also, like I said earlier, write this as kilograms per liter if you wanted to, but usually you'll probably see this specifically in the form of cubic meter. Force, being mass times acceleration, is going to be kilograms times meters divided by seconds squared. That's the unit for acceleration. So kilogram meters per second squared is kind of a pain to say, so we're going to nickname that the Newton, named after Isaac Newton. This guy. Likewise, current, charge over time, is coulombs, unit for charge, per second, unit for time. We're going to name that the ampere, after this guy. Magnetic field is going to be amperes per meter. So sometimes your base units can build each other up too. Or sorry, excuse me, derived units can build each other up too, right? Ampere is a current which is itself a base unit, and it's being combined into a derived unit for magnetic field. So we could write Tesla as amperes per meter, but the ampere itself is coulombs per second. So we could also write this as coulombs per second per meter. So this ends up getting a little bit messy in a hurry, which is a part of the reason that we use our scientist names, like Tesla, my favorite over here for magnetic fields. But this is also really useful for us because what this means is because all of our derived units are made of base units, that means as long as we keep everything in standard format, we'll be okay. So it is a good idea to instantly, as soon as you see any measurement, convert whatever it is into base units, which is going to be represented in this class by MKS, which is the meter, the kilogram, the second. So MKS format means every single measurement you get, put it in meters, kilograms, seconds, and instantly we are in good shape. If I give you a force in newtons, because Newton is made out of those base units, and I'm asking you to solve a question for a mass, for instance, that mass will automatically come out in kilograms. So in other words, my point is, if you put in to an equation every unit in the proper format, it'll come out in the proper format too. So make sure you're using the base units and the standard format of the derived units in order to make sure that the units of your calculation come out in the proper format. And you can do a little trick here to check your answers too, where when you're rearranging an equation or something, you can put them units in and get them to cancel out, and they'll end up being the same. So that is helpful to make sure that we're doing operations and math that are legal and not cheating. Squaring something that shouldn't be squared, dividing by something that you shouldn't divide by, subtracting when you should have multiplied it, etc. Okay. So basically, point is, MKS is what we want, meters, kilograms, seconds, and then we want to make sure that all units in an equation go in standard form. That way they will come out in standard form too. All right. So how do we convert units? Well, for a metric unit, it's base 10, so it's really easy. Everything is just going to be done by multiplying or dividing by factors of 10, kind of like with scientific notation. Otherwise, we're going to be using a conversion factor. So we have conversion factors. Basically, we know, for instance, that 1 day is equal to 24 hours. So we can write that as a fraction, and we can write that in either case. So I can put day on top, hours on the bottom, or hours on top and days on the bottom. These are mathematically equal to each other, and they're also both equal to 1. So we can multiply anything by a conversion factor as long as that conversion factor is correct, and use this to manipulate our units into the proper format. I'm almost certain all of you have done this in previous classes, but it's good to review. So metric prefixes. Like I said, the metric system is base 10. Every conversion is used by orders of 10. So for instance, a kilogram is 1,000 grams. A centimeter is 1/100th of a meter. Right? So these are modifiers that we can add to a unit in order to multiply it by that factor, basically. Multiply it by that conversion factor. So an example I like to give of this with my high schoolers is giga means 10 to the ninth, or a billion. If you call me giga stupid, you're saying I'm a billion times stupider than a guy who is just regular stupid, right? All this word means, all giga means, is that you're multiplying whatever by a billion. So a giga liter is a billion liters. Okay, so that being said, we can use this to manipulate our units into more manageable chunks. So for instance, if I wanted to measure the distance between Earth and the moon, I would use kilometers instead of meters because I'd be dealing with more manageable numbers. If I wanted to measure something like the length of my fingernails, I'd probably use centimeters. If I wanted to measure the wavelength of light, like ultraviolet light, like we looked at earlier, I'd use nanometers. So based on what we're looking at, we're going to change the unit around so that we get less cumbersome units. There is a memory hook that you've probably heard before. That is, King Henry died by drinking chocolate milk. You can use this to easily convert between the most common units, these 6. That is 1,000 times more and 1,000 times less than our base unit. And you can do this in shorthand by moving your decimal point around. So if I want to go from, for instance, kilometers to meters, I can do a trick by moving my decimal point 1, 2, 3 times to the right, just like we did for scientific notation. So for instance, let's say I've got 53 kilometers in meters. That's going to be 1, 2, 3, fill these in with zeros, 5,300 meters. So that's kind of a shortcut that you can use to easily convert between the common ones, which are 1,000 times more or less than a base unit. Okay, let's do another example question. I'd like for all of you guys to pause the video right now and please convert all of these measurements into their base MKS units. So we have wavelength of ultraviolet radiation, volume of a raindrop, mass of Mount Everest, and age of the Earth in different units. Please put those into their classic MKS format. I'll see you when you are done. Okay, so let's go over the solutions to the last question. The first part asks us to find the convert the wavelength of ultraviolet radiation into base units. That's going to be in meters. So we're going to be going from 215 nanometers into meters. Now, nano means billionth. So we can say that 1 billion nanometers, or 10 to the 9th nanometers, equals 1 meter. And we can write this fraction as either this or as this. So billion nanometers per 1 meter, or 1 meter has a billion nanometers. Now, we're going from nanometers to meters, and the classic way that you solve a conversion like this is by going diagonal with your units. So we want to use the version of this fraction that will put our unit that we have on the bottom and the unit that we want on the top. So we're going from nanometers to meters. So we're going to use this version. So it's going to be this times 1 billion nanometers on the bottom, 1 meter on the top. Nanometers and nanometers will cancel out, and we end up getting 2.15 times 10 to the negative 7th meters. Now, also to solve this, if you wanted to, you could have just as easily multiplied your multiplied 215 by 10 to the negative 9th, because 1 nanometer is 10 to the negative 9th as well. So that would work just the same for this question. Okay, let's look at the next example. That is volume of a raindrop. That is 0.05 milliliters into liters. We know that 1 liter, according to our chart, is 1,000 milliliters, which we can also write as 1,000 milliliters being 1 liter. We can phrase this fraction either way. We want to pick the version that will put the units we want on the top and the units we're getting rid of on the bottom. That's going to be the first one. Oopsie. It's going to be this one. So we could say 0.05 milliliters times 1 liter over 1,000 milliliters. Milliliters cancels milliliters. We end up getting 0.00005 liters. We could also write that as 5 times 10 to the negative 1, 2, 3, 4, 5 fifth. Okay, so now we have the mass of Mount Everest, which is 810 quadrillion grams. So it's going to be 810 quadrillion. Quadrillion is going to be times 10 to the 12th grams. We want it in kilograms. So we know that 1 kilogram is 1,000 grams, which is the same as saying there are 1,000 grams in 1 kilogram. I want kilograms on top and grams on bottom, so we're going to use this version of that fraction. So I can say 810 times 10 to the 12th times 1 over 1,000. And we're going to end up getting 8.10 times 10 to the 6 times 10 to the 12th. Divided minus 2 is 10 for putting it next to the 8. Divided by 1,000 is going to be another 3, so that's times 10 to the 7th kilograms. And then lastly, approximate age of the Earth is 1.432 times 10 to the 8th gigaseconds. So in 1 gigasecond, giga means 10 to the 9th, there are 10 to the 9th seconds. Meaning there are 10 to the 9th seconds in 1 gigasecond. I should have written it like this, it's easier. Also, technically it's capital G for giga, if I want to be a stickler about it, which I should be. Okay, so we want seconds on the bottom, or sorry, we want gigaseconds on the bottom, seconds on top. That's going to be this version of the fraction. So we can say 1.432 times 10 to the 8th. We're multiplying this, sorry, that's gigaseconds. We're multiplying this by the fraction 10 to the 9th seconds over 1 gigasecond. Gigaseconds cancels. And by the way, when you're adding or multiplying numbers in scientific notation, you're going to be adding your orders of 10. So this is the same as saying 1.432 times 10 to the 17th. So that's the age of Earth in seconds. Okay, let's try another question. Very similar to the last one, only this time we're going to be doing more complicated stoichiometry than just orders of 10. So the sun moves a total distance of 584 million miles around the sun in 1 year. Please convert this speed from miles per year to meters per second. You are probably going to have to Google some stuff in order to figure this one out. So please pause the video right now and try to solve this problem on your own, and then come back in a minute and we will discuss how we can solve this problem. Okay, welcome back. Let's solve this problem. So in this question, we're converting 584 million miles per year to meters per second. So let's figure this out. We are moving 584 million, which is 6 zeros, miles in 1 year. Now we want the top in meters and the bottom in seconds. We're going to have to use conversion factors for this. The years part will probably be easiest to get rid of first, so let's do that. But you could do it in the other order too if you wanted. All right, so I'm going to multiply this by my conversion factor. I don't know off the top of my head how many seconds are in a year, but I do know how many days are in a year. And so we can convert years to days using that conversion ratio. I have years on the bottom here, so I want to put years on the top here. And then we're going to put 365.25 days on the bottom. Years cancels years. Now we have miles per day. Cool. Okay. Next, let's try this again. I want seconds, remember. Days. I don't know days to seconds, but I do know days to hours. So I could say that in 1 day, there are 24 hours. I'm going to put it in this order so that my D's cancel and my time unit is still on the bottom. So I now have 24 hours on the bottom. I want that in seconds, like I said. So we're going to multiply this. In 1 hour, there are 60 minutes. That cancels my hours. And then there's 60 seconds in a minute. I'm going to put minutes on top. Like this. So now all my units are canceling, going diagonal, and I have seconds on the bottom. Perfect. So now I've got this in miles per second. I want this in meters per second. So I don't know the conversion ratio for miles to meters. However, I do know the conversion ratio for miles to kilometers. And this is the value I was talking about in the problem that you'd probably need to look up. Okay, so miles is on top, so we want miles on the bottom. And we're going to put kilometers on top. And I know that in 1 mile there is 1.6 kilometers, more or less. So miles being diagonal to miles, we'll cancel it. Now we have kilometers on top. We can then multiply this fraction from kilometers to meters. I want kilometers on the bottom. I want meters on the top. So we know that a meter is 1,000 kilometers. Kilo means 1,000. So now notice I have meters on the top and I have seconds on the bottom. So all my units except for my meters and my seconds are gone now. So now the last piece is pretty easy. All I have to do is just multiply everything on the top across and then divide everything on the bottom. Okay, so that's going to be, let me grab my calculator really quick. Hey, what's up, guys? Editing room Asa here. So past Asa actually made a mistake while he was recording this. He said that the conversion factor for meters to kilometers was backwards. 1 kilometer is 1,000 meters. 1,000 meters is 1 kilometer. He kind of stumbles around a little bit here trying to figure out why his numbers aren't working out. And it took me about a minute or so to like figure out what was going on. So I've just sped this part of the video up so you don't have to waste as much of your time. But just so that you know, I did correct it later and I'm going to skip to that part right now. Oh, pardon me. I'm so sorry. I made a mistake earlier. I'm going to leave this in because this might be similar to a mistake that you guys might make. I got my conversion ratio for kilometers and meters backwards. There are 1,000 meters in 1 kilometer, excuse me. So actually our number on top is higher by an order of 1,000. So that's 9.34 times 10 to the 11th. That sounds a lot better. Apologies. But it's a common mistake to make. Sometimes you'll get your conversion factor backwards. Some of you might have even done this. So it's good to leave this in the video just so that you can see a common mistake that people might make. 9.34 times 10 to the 11th meters. And then on the bottom is going to be 1 times 365.25. By the way, 365.25, some of you probably already know this, but the Earth's orbit around the sun is not exactly 365 days. It's actually 365 and a quarter days, which is why we have leap years. So putting that into my calculator is 31,557,600 seconds. So now all we have to do is do that last division. I can write this as 3.94, or sorry, 9.34, excuse me, times 10 to the 11th, divided by 31,557,600. And we end up getting about 29,596.7. meters per second. So that is how you solve a problem like this.